Okay, hello. This is Chapter 11, Fundamentals of the Nervous System and Nervous Tissue. So the nervous system's function is to gather sensory input, to process that in the brain, and then send an output to the muscles for an action. The central nervous system is made up of the brain and the spinal cord, while the peripheral nervous system is made up of cranial nerves, spinal nerves, and ganglia. The peripheral nervous system can be divided into an afferent division, which is going to be the sensory input, and an efferent division, which is the motor division for conducting impulses from the CNS to effectors like muscles and glands. Now, the motor division can be further divided into the somatic and the autonomic nervous system. The somatic nervous system is voluntary side of nerve fibers, and this conducts impulses from the central nervous system to the skeletal muscle. The autonomic nervous system, which we'll get into more in subsequent chapters, I think chapter 13, involves the visceral or involuntary nerve fibers, and this conducts impulses from the central nervous system to the muscles like cardiac muscle, spoob muscle, and glands. The autonomic nervous system can be further divided into the sympathetic or the parasympathetic. Sympathetic would be to mobilize body systems during activity, and the parasympathetic would be to promote housekeeping functions during rest. So the most abundant cell type in the central nervous system is called neuroglia. It's not the neurons, but it's the supporting cells that support the neurons and their function. These are called neuroglia. One of the neuroglia is the astrocyte. And astrocytes, as well as pericytes, make up the blood-brain barrier, which is a very tight barrier that protects the brain from the systemic agents that might be circulating. Another set of neuroglia cells are the microglia. Microglia are the macrophage of the central nervous system participating in defense. So these are the watchmen that will sample the surrounding area and protect the brain from infection and cell debris. There are also ependymal cells. These line the central nervous system cavities, and they create cerebrospinal fluid. And so you have some fluid-filled cavities. So the ependymal cells are part of the glial cells, just like the astrocytes and the microglia, and they produce the cerebrospinal fluid. So the neuroglia also includes the oligodendrocytes. These very specialized cells have processes that form myelin sheaths around the central nervous system nerve fibers. And this insulation is critical to enhance the action potentials traveling down these axons. Schwann cells are the cells of the peripheral nervous system that will do the same for peripheral nerve fibers. Okay, so we take a look at the motor neuron to begin with. And there's this typical shape with a large cell body that has multiple dendrites. These are the receptive regions. So these dendrites would collect information, integrate, and then generate an action potential which is a message, a very quick message that travels down the axon to the axon terminal, where a neurotransmitter would then be released to continue this signal. Now you can see this motor neuron is myelinated. It's got myelin sheaths with gaps. These gaps allow what's called saltatory conduction, or propagation of the action potential. The action potential is able to jump over these areas of insulation, and it greatly enhances the speed of the action potential as it travels down this very long axon. So the direction of the impulse would be away from the cell body to the axon terminal. Here's a nice picture of a neuron. You've got the cell body in the middle. You've got the dendrites, which look like branches of a tree. And then we can see the axon traveling outward. So in the peripheral nervous system, Schwann cells, these are the cells that will myelinate the peripheral nervous system. And they do this by wrapping around the nerve, producing a myelin sheath. So at first, the Schwann cell envelops the axon, then it rotates around the axon, wrapping its plasma membrane loosely around successive layers. As it does this, it tightens up these concentric circles, and this is what forms the insulation, which improves conduction of your action potential. Here's an electron micrograph showing these concentric circles. The cytoplasm has been pushed aside. You've got maybe a nucleus up here. And then in the middle would be the axon of the nerve. So there are three different types of neurons. There's multipolar, bipolar, or unipolar. And these refer to the processes extending out of the cell body. So if we start with the multipolar, there are many processes that extend out from the cell body, and you have a single axon. With bipolar neurons, you've got two processes that extend out from the cell body. One is a fused dendrite, and the other is the axon. Unipolar, also can be called pseudo-unipolar, is when only one process is coming out of the cell body, and it extends to form the central and peripheral processes, which together comprise the axon. So the neuron can be divided into a receptive region, which is in blue here, which would be the cell body and the dendrites, which are going to collect information. And then there's a conducting region, which would be the axon that conducts this action potential, and then the secretory region, which would be the axon terminals that release neurotransmitters to its effector. So just a note, many bipolar neurons do not generate action potential. Okay. So the multipolar are the most abundant type of neurons in the central nervous system. There are variations where you have a different amount of dendrites. We've got a Purkinje cell of the cerebellum on the left and a pyramidal cell on the right. Bipolar neurons are rare. They're found in some special sensory organs like the olfactory mucosa, the ear, the eye. And then unipolar are mainly found in the peripheral nervous system. So the most common class of neuron is the multipolar. There are interneurons which conduct impulses within the central nervous system, integrating sensory input and motor output. Now we talked a little bit about bipolar neurons being the sensory neurons. I show here the eye and a bipolar neuron of the retina. And then unipolar, these other sensory neurons that conduct impulses from the CNS for different types of interpretations. Okay, so there are some very important proteins that we need to go over that are gated channels. So we've got these ion receptors which are embedded in the plasma membrane that are chemically gated. They bind a receptor and they open and allow certain ions to travel through. There are also voltage-gated ion channels that respond to changes in voltage. So they'll open with the depolarization to let certain ions through. Now, neurons have a few very interesting properties regarding their potential difference across the membrane. Neurons are kept at a very low voltage of around minus 70, minus 80 millivolts. These are one of the most hyperpolarized cells in the body. And so what we can do is insert electrodes, place them outside, and insert them in the axon and measure the difference in potential that occurs with the action potentials. As the action potentials travel down the axon, you'll see a change in potential with your voltmeter. Okay, so we get back to ions, and we remember that sodium is in high concentration on the outside of the cell, or the extracellular, while potassium is in high concentration on the inside of the cell. And just an extension of that, the concentration of potassium outside of the cell is very low, and the concentration of sodium inside the cell is very low. And this creates a chemical gradient. So the cell, or the neuron, is permeable to these sodium and potassium ions. Now it's interesting that creation of the resting membrane potential, or this minus 70 or minus 80 millivolt potential difference, is caused by the leakage of potassium out of the cell. Now, as you lose the positively charged potassium, the potential difference becomes greater inside the cell, becomes more negative, because you're losing a positive charge. Now, if you open your sodium channels, you will depolarize, which means you'll go from a negative 70 millivolts possibly all the way up to a positive 30 millivolts, because there's a strong driving force for sodium to enter the cells. There's not only a chemical driving force, but there's an electrical driving force. Now, the membranes can depolarize or hyperpolarize, depending on the type of stimulus. And so the cell is sitting at a resting potential, let's say minus 70 millivolts, which means that the inside of the cell is negatively charged with reference to the outside of the cell, which would be measured as a 0. A depolarization would be movement in the direction towards 0, while a hyperpolarization would be to become more negative. And in a neuron, a depolarization is synonymous with activity, or turning the neuron on, whereas a hyperpolarization would be synonymous with inactivity, or turning the neuron off. As the membrane potential becomes more negative, the neuron shuts down and is unable to create action potentials. Now, when the action potential or graded potential, so you don't have to reach an action potential to have a potential change. There can be sub-action potential changes, like graded potentials, that add up then to produce a certain threshold. But it only involves a small patch of membrane. This depolarization that occurs with action potential down the axon, it's not a global change. It's just a small region of the membrane that depolarizes. A small number of ions are responsible for this depolarization. And the depolarization will move then down the axon, and behind it, the area will then repolarize. So it's a wave of depolarization that moves down the axon very rapidly. And this is your signal. So the depolarization spreads, opposite charges attract each other, creates a local current that depolarizes the adjacent membrane areas, spreading the waves of depolarization. Now, this direction of depolarization is one directional, it's unidirectional, and that's because of a refractory period, which we'll talk about in just a second. This signal, the action potential, will decay with difference because membrane current is lost through having leaky membranes. So myelination will help this and will help to speed up the action potential. So let's look at the different phases of the action potential. We start with our resting phase where the sodium and potassium channels are closed. Now you have your potassium leak channels. It's a little bit different than an outright potassium channel that opens and lets the potassium efflux out of the cell. The potassium leak are going to establish this resting membrane potential. Then sodium channels open, allowing for sodium entry. This is a chemical gradient as well as a charge gradient. And so the cell will depolarize this patch of membrane toward positive 30 millivolts. The sodium channels then close and the potassium channels open. At this time, the sodium channels are not only closed, but they're inactivated, meaning they cannot activate even with a greater stimulus. So once the potassium channels open, potassium effluxes, and the membrane potential returns to its negative state, but there's a little after hyperpolarization where the cell will dip even more negative for a small period of time before it goes back to its baseline. This is your action potential. It travels down the axon. It's going to be a binary type of communication where you have no signal, and then a signal, and then no signal, and then a signal. So it is a yes or a no response that produces very distinct signals. So the key players are sodium channels and potassium channels that when they open, the sodium channels will allow sodium into the cell, causing depolarization, and when the potassium channels open, cause potassium efflux out of the cell, which causes the repolarization. Okay, conduction of this action potential is very rapid. It might take 2 milliseconds for the cell, once its sodium channels open, for it to depolarize from minus 70 to around positive 30 millivolts. It reaches its peak, then a few milliseconds later the potassium channels open and you get your hyperpolarization. So it's very rapid. We're talking in the course of 6 milliseconds, we would get our action potential on a very distinct patch of cell membrane. Now these action potentials, as I mentioned, they are binary, and so they are on or off. There is a threshold that must be achieved to create the action potential. Once you achieve your threshold, there's no going back, and this axon is going to depolarize, and this action potential is going to travel very rapidly down the axon. Now you can see in this top figure, you've got bop, 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 and then a break, and then bop, 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 bop. And so we have different frequencies. That can be part of the signal, but it is a yes or a no response. It is simply going to activate once threshold has been achieved. Now this threshold does not change unless you're in the refractory period or in a disease state. So the sodium channels, after they open and allow sodium entry and subsequent depolarization, they enter a period of time where they cannot further open. And so once they close, they are in refractory. It's called an absolute refractory period, where even a greater stimulus will not cause another action potential. Now this does a few things. It establishes unidirectional action potentials, and it protects the neuron from becoming too active. Then there is a relative refractory period in which a greater stimulus can create another action potential. So the threshold for the absolute refractory period, there is no threshold for it. But for the relative refractory period, the threshold is greater than the baseline threshold to get that first action potential. Now, without the myelin, which we talked about with our supporting cells and our oligodendrocytes, which are going to myelinate the central nervous system neurons, the Schwann cells, which are going to myelinate the peripheral nervous system neurons. The myelin promotes propagation of its action potential. If you have a non-myelinated fibers, the voltage or the action potential is going to decay over time and distance. So in non-myelinated axons, the conduction is slow. And in myelinated axons, the conduction is fast. The reason it's fast is what I mentioned before. It's called saltatory conduction, but the depolarization can jump the myelin sheath. It just hops right over it and then depolarizes in between, and then it hops over that next myelin sheath. And so it jumps over these myelin sheaths, which greatly increases the speed of conduction. Okay, so at the cell body, there are different ways of stimulating this neuron. There can be axodendritic synapses or axosomatic synapses or axoaxonal synapses. And what you're looking at are synapses on the cell body, on the soma, which would be axosomatic. The cell body is also called the soma, cell body. You can have impulses that integrate onto the dendritic synapses directly. And you can even have impulses that modify the potential of the axon itself. These are the axoaxonal synapses. So different places on the neuron that you can get synapses: on the soma, on the dendrites, or on the axon. Once the action potential propagates down the axon, you get to your synapse, which is going to be, for example, a motor end plate or another neuron. But we have a chemical synapse that will communicate from one neuron to the next neuron through release of a neurotransmitter. And you can see the presynaptic membrane, which is made up of this neuron, this presynaptic neuron. And then here we show a postsynaptic neuron with the postsynaptic membrane. In between is the synaptic cleft, where the neurotransmitter is dumped. Now, this exocytosis of the neurotransmitter is a calcium-dependent process. Voltage-dependent calcium channels open in response to the depolarization of the action potential down the axon into the terminal. These are what's going to cause exocytosis of the vesicles into the synaptic cleft, which will then stimulate this postsynaptic neuron. So the first step is the action potential arrives at the axon terminal. Then voltage-gated calcium channels of the axon terminal will open. Calcium entry causes the synaptic vesicles to release the neurotransmitter by exocytosis. The neurotransmitter diffuses across the synaptic cleft and binds to its receptor on the postsynaptic membrane. Now, this binding of neurotransmitter to its receptor will open ion channels and result in certain graded potentials that could then be added up to reach a threshold themselves. The neurotransmitter will then be mopped up, and this connection will then be closed. So neurons, when they signal to other neurons, they signal the neuron to fire. Now, there can be inhibitory signals also that will signal it to shut down and to stop firing. The different signals that can be reached, the first one is called excitatory postsynaptic potential, but we're at the postsynaptic membrane. This is an excitatory potential difference, which means you're going to get depolarization. If it doesn't reach threshold, it just goes back to its resting membrane potential. There can also be inhibitory postsynaptic potentials, where the neuron is hyperpolarized, and this is the neuron shutting down, because with each distance from the threshold, it's going to be harder to reach threshold then. And it'll take more graded potentials to come in to summate to reach threshold before another action potential is created. So the excitatory postsynaptic potentials and the inhibitory postsynaptic potentials add up. There can be temporal summation, which is within time. If a number of excitatory postsynaptic potentials come in and the soma is able to reach threshold, it will activate another action potential. There can be spatial summation, where a certain area is allowed to depolarize. So the net effect is the summation of excitatory and inhibitory postsynaptic potentials that, when they achieve threshold, will then activate another action potential. So if we compare the graded potentials and action potentials, graded potentials are in the cell body and dendrites, where the action potentials are at the axon. Graded potentials cover short distances, maybe from the soma to the initial segment of the axon, or from the synapse, the dendrites to the initial segment. Action potentials, however, start at the axon and they travel long distances. They will go all the way to the synapse. Graded potentials have a lower amplitude. They're the smaller potentials that will then add up to create an action potential. There's no positive feedback for graded potentials, and they dissipate over time. But action potentials are self-propagating. There's positive feedback, which will regenerate the action potential at each different segment of membrane. During repolarization, when there's no graded potentials, the membrane will return to its resting state, whereas with the action potential, it is a positive feedback situation where your potassium channels and sodium channels open, allowing this action potential to propagate. So we've got temporal and spatial summation leading to the action potential. So the function of the excitatory postsynaptic potentials is for short distance signaling, usually within the soma. The depolarization spreads to the axon hillock, and it moves towards threshold to generate an action potential, whereas the inhibitory postsynaptic potentials, they're also short distances, but these move the membrane potential away from threshold. So this figure summarizes again: when you depolarize, you open your sodium channels, allowing sodium to influx. This is going to depolarize the membrane from around minus 70, minus 80, minus 90 to positive 30 or positive 50. Then these sodium channels will close, and the potassium channels, which are a little slower to open, they open next, allowing repolarization, and you get this after hyperpolarization, and then back to your resting membrane. The different types of receptors cause rapid synaptic transmission. So we'll take a look at the different proteins that are opened, usually ligand gated, which would be maybe a neurotransmitter that will open up this channel. There are also G protein linked receptors, and this is part of an intracellular secondary messenger system. G proteins bind GTP, cause intracellular second messengers, which allow for amplification. So this is after neurotransmitter binds. There can be different ways of amplifying the signal through G proteins. So the first step would be the neurotransmitter binding through its receptor. The second step activates the GTP binding protein. GTP then binds to a protein called adenylate cyclase, which is going to create cyclic AMP, which is a very important intracellular messenger. And this CAMP then can open or close different ion channels accordingly, as well as to activate various enzymes and genes. So neurons are pooled to create responses. And there are different zones of activation: a facilitated zone, a discharge zone, and then back to our facilitated zone. This is a simple neuronal pool. Okay, so let's look at a reflex arc, because this will introduce an interneuron. So we've got a receptor that synapses in the central nervous system. This could be a sensory neuron. There's then the integration center in the spinal cord, which involves an interneuron. This could be excitatory, this could be inhibitory. If it's excitatory, it'll activate a motor neuron, which is going to then activate the effector or the response. This is a simple reflex arc, which means that the activation or the depolarization that is caused does not need to be processed by the brain. You can get a response directly through an interneuron, so it's a very rapid way of communicating. An example would be to withdraw your hand from a hot stove, where you activate your effector muscle before you even have time to think about it. So it's a reflex. This is going to be a subconscious process. Let's take a look at the different types of circuits in neuronal pools. There are some circuits that are diverging, where you have one input and then many outputs. An example would be a single neuron in the brain can activate 100 or more motor neurons in the spinal cord, and then can activate thousands of motor neurons in the skeletal muscle fibers. Allows different levels of recruitment. There can be converging circuits where you have different neurons that converge on a central neuron for the output. And then there can be reverberating circuits where you can get amplification or oscillation. Examples might include breathing or the sleep-awake cycle, or during repetitive motor activities such as walking. There are parallel after discharge circuits where you have parallel neurons that are activated by a certain input, and these produce a various output. Okay, that is the chapter in a nutshell. I'll see you for chapter 12, where we talk about the anatomy of the nervous system.